The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to today's webinar. Today during the webinar we hope you'll learn how Pointwise can save you time building high-quality meshes for turbomachinery CFD analysis. We're going to be doing a live demonstration of building a structured grid for an axial pump and setting up an open foam analysis. I'm Rick Matus, Vice President of Sales and Marketing at Pointwise. I'm going to give a brief introduction and I'll cover a few ground rules for the webinar. First, the schedule. The live demonstration will take about 30 minutes. During the demonstration, you won't be able to ask any verbal questions, but you'll be able to type questions into the question window, and we'll answer them as best we can during the demonstration. After the demonstration, there'll be time for verbal discussion, so if you're more comfortable talking instead of typing, that'll be your chance to ask some questions. Dr. Chris Sidoroff, Pointwise Sales Engineer, will be conducting today's live demonstration. Chris earned his PhD in mechanical engineering at Syracuse University in the area of personal microenvironment analysis. He used GridGen for a lot of his graduate research, and since coming to Pointwise, he's quickly become an expert in using the Pointwise software as well. Your written questions will be answered by Nick Wyman. He's Director of Applied Research at Pointwise. Nick has worked extensively in the turbomachinery field for many years, from work on his master's degree at Texas A&M to developing the original turbo grid while he was at ASC, and many years developing grids, automated scripts, and gridding techniques while working at Pointwise. Now I'll turn things over to Chris to begin the demonstration.
Okay, thanks, Rick. So the goal of my demonstration today is to show how Pointwise meshing techniques can help you deal with difficult features of complex turbomachinery geometries. As Rick mentioned, I'll be demonstrating how Pointwise was used to create a high-quality multi-block structured mesh on an axial pump. And the actual geometry is the DARPA HIREP pump used in a very comprehensive experimental study at the Penn State University HIREP facility. The original geometry and experimental data are part of the Journal of Fluid Engineering database. So while I'll be showing Pointwise's structured meshing capabilities today, Pointwise is a comprehensive CFD pre-processing tool. It has a wide range of both advanced structured and unstructured meshing tools. Some of these techniques are unique to us. The software includes both of them. There's no add-on modules for either or. You choose what type you want to work with and switch by simply clicking a mouse. Even though there are some advanced meshing techniques, Pointwise's interface is designed in such a way that they're easy to use, and something you'll see me frequently do today. It has many tools for importing, creating, and modifying geometry. It has two methods for working with the geometry. The first, which I'll show today, is something we call fault-tolerant meshing. That allows you to heal the mesh over faulty geometry, and you fix the errors on the mesh level. The other, called solid modeling, allows you to heal geometry in a more traditional manner. And these two techniques are not mutually exclusive. They can be used together to fix the mesh. And lastly, something I'll cover toward the end of the demonstration is Pointwise's flexibility when it comes time to export your mesh to your CFD solver. But again, my objective today will be structured meshing and dealing with some dirty geometry. I'll begin by discussing my overall topology strategy, then get into how I dealt with the fillet and tip gap regions. Next, I'll show you how you can work with and around dirty or missing geometry, and this is where I'll show how the fault-tolerant meshing works. I'm going to wrap things up by showing Pointwise's flexibility for setting up the mesh for your CFD solver. So I want to start by briefly describing the basic characteristics of the HIREP geometry for those who aren't familiar with this case. So the flow direction, so I'm showing Pointwise's display window here. The flow direction is from the left to the right through the inlet guide lanes. I'm just going to use IGV from short from now on, and on through the rotor. The diameter of the shroud is 42 inches. It's a little bit more than a meter, and the hub diameter is 21 inches, about half a meter, and the rotor RPM is 260. So the most obvious feature is the three-dimensionality of the rotor blades, designed with significant circumferential lean such that the suction surface points towards the hub. I'll just reorient it to show what I'm talking about. So you can see how there's the lean on the rotor blades. Another obvious one is the fillets on the IGV on the rotor blade and also at the tip of the IGB, and in particular where they meet the end walls. And a couple of the less noticeable features are the chiseled trailing edges on the IGB and rotor, and the rounded corners of the rotor blade tips. And I'll just change to a different orientation to show what I'm talking about. So we can see the rounds on the tip of the rotor, and then a very small chisel along the back side of the rotor blades, and there's a similar one on the back side of the IGB. It's the combination of these characteristics that make this a challenging geometry for a structure mesh, and it's particularly true for the rotor blades. Before I show you the mesh, one constraint I imposed on myself for this mesh was to keep a one-to-one point matching on the periodic boundaries, as not all CFD solvers have the ability to handle many-to-one periodic boundaries. And since I'm going to publish the grid that I'm going to show you today, I want it to be usable by as many CFD solvers as possible. So here's the final mesh. You can't see the internals of the mesh here, so I'm going to show you what the interior of the mesh looks like. I'm going to start by looking at the IGV. We're just going to use the examine tool to look inside the mesh. Let's select a cutting plane and then reorient this view so we can see a slice through one side of the blade patches on the IGV. You can see the packing near the shroud and the hub and near the blade. And then I'm going to, maybe I'll switch and let's look at the actual rotor blades themselves. Again, I'll just take another topological cut. I'll just look down the axis again, just to give you a feel for what's going on. So the three-dimensionality of this mesh makes it somewhat tough to explain my overall topology layout and why I chose that topology layout. So what I'm going to do is I'm going to switch to a simplified schematic to help describe the topology I used. So I'm going to start from the beginning and begin by discussing the IGV topology. So I'm looking radially down the stacking line of the blade, and you can see I chose to use a basic 3-block layout. There's no O block around the blade to resolve the boundary layer, and then I have an H block on either side of the blade passage. You can see I just have it marked as H and H. So I want to use a simple topology because it's going to make it easier to modify the mesh later on when I want to change the resolution of the mesh, or maybe even tweak the geometry for some subtle changes in geometry. However, a common problem with H blocks laid out like this is you often get shearing when there are sharp changes in the shape of the block, and this is pretty common at leading and trailing edges like I'm kind of pointing out here. So let me show you how Pointwise's elliptic smoother can let you keep the simple topology I'm describing here and eliminate the shearing. I'm going to flip back to a Pointwise to show you what I'm talking about. So what we have here are the curves that represent the mesh on the hub of the IGV. And the first thing I'm going to do is I'm just going to quickly show you how to assemble the meshes on the hub surface. And I'll do it for the other side. And I'll just reorient just so we can look straight down on top. So the initial mesh is created using the transfinite interpolation method, but as I mentioned, when there are sharp changes in the block, it can cause a lot of skewness, and this is pretty obvious that here, like I mentioned before, with shearing at the leading and trailing edges. So I'm going to use Pointwise's grid solver to fix that. So I'm going to select the two surface meshes I just made. And it's the edge attributes panel where I have complete control of what I want to happen when I run the solver, spacing, orthogonality, and behavior on the boundaries. So I definitely want to smooth the grid along the blade. So I'm going to fix the other edges and only smooth the mesh along the blade. I go to solve, and I run it for a few iterations. And if I zoom in here a little bit, we can see how much it's definitely improving, you know, at the leading edge and very similar to the trailing edge. It looks a lot better, like I mentioned, at the leading and trailing edges, but you can see there's a fair amount of skew still in the middle part of the passage, about mid-chord. Ultimately, we'd like these grid lines to run somewhat orthogonal across the middle of the passage. So to fix that, I'm going to let the points on the periodic boundary float. So I'm going to go back to the Edge Attributes panel. I'm going to fix everything again, except for I'm going to change the boundaries to orthogonal, and that's going to allow the points to float such that the grid lines will become orthogonal. I'll change the angle again to orthogonal. In this case, I have to run it a few more than 10 or 20 iterations, so I'm just going to increase it just to show what I'm talking about. So we can see now it's sliding the points along these lines to achieve much better orthogonality. If I just zoom out, we can see the full mesh. So at this point, the surface mesh looks much, much better. So I'm just going to take a quick look at it in the Examine tool. I'm going to look at minimum included angle. And we can see that whereas before, if we look at minimum included angle, we would have had minimum angles, you know, less than 1 degree. And now we can see we have them between, you know, 33 and 90 degrees. Something I haven't really mentioned yet is that the solver works with surface constrained meshes. So even though this is a 2D mesh, the mesh can be constrained to a 3-dimensional surface and stay attached to that surface when I run the smoother. So if I just rotate the orientation, you can see that there is some curvature due to the hub in this case. So I'm going to flip back to the final mesh to see how I effectively use the smoother in several locations. So here's the final mesh. Again, if I'm just going to reorient the view looking straight down, you can see what I did on the IGV hub. You can see similar sort of idea on the rotor hub as well. Just going to reorient my view, and I'm going to show you how it significantly helped things at the inlet and outlet. So if I just turn on the display of the grid lines and the inlet of the rotor, just highlight so it looks a little easier for you to see. And you can see how the grid lines are very orthogonal near the hub and the shroud, and then they transition very smoothly into the middle part of the passage. So the strategy I just demonstrated works really well for the IGV, but it kind of falls apart somewhat when trying to use it for the rotor. So let me show what I changed for the rotor. I'm going to flip back to my simplified schematic to continue my explanation. So as you can see, due to the orientation of the rotor blade, trying to use a constant theta plane for the periodic boundaries is probably not going to work. So a better approach is to use a Z shape for the rotor blade passage. So what I did was I offset the inlet and outlet domains so they're somewhat centered with the leading and trailing edges of the blade. And a further tweak that I made to the rotor topology was to add a couple of small H blocks, again at the leading and trailing edges. And without doing this, I found that the sharp changes in the block shape made it very difficult to get a good quality mesh, even using the elliptic smoother. So I'm going to flip back to the final mesh to, again, just to key in on how things look on the actual rotor blade. So you can see here I'm going to zoom in a little bit toward the leading edge of the rotor blade, and you can see, so we can see the topology I use here. I'm selecting kind of the 3 blocks that I mentioned before. There's a small one at the leading edge, and then the 2 H blocks in the blade passage. So what we have is a very smooth, very orthogonal mesh with grid lines, aligned with the flow path through the passage, and it's really the power of the elliptic solver that allows you to keep this simple topology. You don't have to rely on all sorts of elaborate topologies to get a high-quality mesh. So I'm going to switch gears now and talk about how to mesh the fillets without disturbing the topology I discussed before. Again, I'm going to use my schematic to help with the explanation. So now I'm looking down the axis at the blade, but I'm going to start without the fillets just to help with the explanation. Again, we have the O block around the blade and the H blocks in the passage. And if I turn on the horizontal lines, they delineate the boundary layer region I want to get at the hub and the shroud. So you can see without fillets, getting an H block in the corner region is pretty straightforward. It clearly matches up with the H block idea. Now if I include the fillets, here I'm showing them at the root and the tip, as is the case with the IGV, and I turn on the horizontal lines that delineate the boundary layer region, we can see how the fillets are going to make this somewhat difficult to use an H block because the curvature of the fillet. What we want is for the grid lines to follow the hub, follow the curvature of the fillet, and then up vertically along the blade, and all while having a tight normal spacing to resolve the boundary layer. So what I'm going to do is I'm going to use a simple example in Pointwise to highlight the problem where trying to get an H block in the fillet is pretty tough, and I'm going to show you a technique to solve that problem. So I previously created some curves in Pointwise that represent the topology I was just talking about. Here I'm just showing half. So to make an H block in the fillet, the first thing I need to do is split the fillet curve so that I have full curves that represent the four sides of the structured mesh. Now I'm going to go ahead and assemble the mesh. Before I adjust the near wall spacing, I'm going to zoom in a little bit closer to the fillet at that split point. You can see how the H block topology really doesn't work. You can see how the grid lines kind of want to wrap around the point where I just split the fillet curve at. And it's going to be particularly exaggerated when I adjust the mesh for the near wall spacing. So I'm going to go ahead and do that just to show you. So on the blade and the hub, everything looks really good, but now it's really, really bad, particularly at that split point in the fillet. So just to really kind of cap it off to show you, I'll look at and examine. We'll look at minimum included angle in that fillet block. And you can see we have a minimum included angle below 1 degree, so this is just not acceptable. And no matter how much I try to smooth it, the block is not going to work. So I'm just going to do what I just did and show you a better approach for getting a high quality structured mesh in this fillet region. So the first thing I'm going to do is I'm going to use a pole to create an O block in the fillet. For those of you who don't know what they are, poles are just grid lines with a zero length but have a finite number of points. And you may also have heard them referred to as singularities. So I'm going to create my pole at the intersection of these two grid lines. Now I'm going to go ahead and assemble the mesh. And let me just adjust the near wall spacing. So already at this point, the grid looks a lot better than the H block approach, but poles aren't what we'd want for a couple of reasons. First, and maybe the most obvious, is maybe your structured solver just doesn't support poles. This typically isn't a problem for unstructured solvers because the cells around the poles are converted to wedges. But another issue that the pole, in this case, introduces a large jump in cell size. And just to highlight that, if I were to select the 4 blocks and we look at, like for example, we'll look at area ratio, you can see how there's a fairly large jump, a very, very large jump from the H block above the hub into the fillet block, and then up to the blade block. And so we'd like to maybe look at a different approach for fixing this. So let's just get out of examine. And furthermore, we'd like to improve the mesh in the fillets, because more often than not, a lot of the really interesting flow features occur in these regions, and so we really ultimately need a better quality mesh here. So to eliminate the pole, I'm going to create an OH topology in the fillet region. So to do this, I'm going to first of all split the pole block. Split it at a J line. Now I need to split this curve. Now I can delete the pole, and now I have these 4 new curves that I can use to create a small H block in the fillet region. So, as I showed you before, H blocks in these circular sector regions don't work very well, but the boundaries of this H block are kind of internal to the mesh, and so I'm going to show you how to use the elliptic smoother to fix that. So I'm going to pick these two blocks in the fillet region. I'm going to go to the grid solver, back to our powerful edge attributes panel, and I'm going to change the boundary condition. Now I'm going to change them to float, and what the float does is it allows any of the internal grid curves, in this case it's the boundary between these 2 blocks, to float to achieve a better quality mesh. And one additional, I'm going to kind of fix the rest of the grid. Excuse me, I'm going to leave it till orthogonal, but what I want to do is I want to fix the spacing in the fillet near the wall, just so we keep our 0.001 spacing. So I'm going back to solve, and we'll just run it 10 iterations. Now if I get out, and we can see how now those internal grid curves that were circular before have now changed to kind of like behave like internal grid lines. And just to show you that indeed the mesh quality is improved, I'm going to go back to the examine tool and look at minimum included angle. And now we don't have any, we have no cells that are less than 50 degrees minimum included angle. So this is, I'm done here with this. So really what I showed you is a very high quality mesh in the fillet, can be made in the fillet, and really few changes need to be done to our overall topology. For the full mesh, it really only took me about 5 minutes to convert the pole blocks in the fillets to OH on both the IGB and the rotor. And actually I have a version of the mesh saved prior to the conversion of the pole blocks to the OH style. And I did this because it's easier for me to modify my near wall spacings later if I want to refine or coarsen the mesh near the walls, and then I can quickly convert them to OH. And I'd probably even write a script to automate it for me if I was going to use these kind of grids a lot. Now before I move on, I want to switch back to the full mesh and show you some slices through the IGB mesh to show you how it turned out in 3D. So again, I'm just going to turn on a topological cut here through the IGB mesh. I'll just zoom in a little bit at the base of the IGB blade. So in this case, we can see that the similar sort of approach was taken here, except I did this. I followed the steps in 3D. It's very analogous to what I showed you in 2D. So the next difficult area is the tip gap on the rotor. So let me move to that location to show what I'm talking about. So here I'm looking upstream at the back side of the rotor blade. Tip gaps are another key feature to include when trying to predict the performance of a turbo machine. Tip leakage is a pretty important loss mechanism, so we'd like to simulate the flow in the tip gap region. So first, if I just temporarily disable the mesh, and I'm going to turn back on the geometry. It's difficult to see here, but if I zoom right into the small details of the trailing edge of the tip, you'll see that there's actually a hole in the geometry, and particularly it's just the nature of the geometry itself. It's kind of dirty here. It's a little bit difficult to work with. And I'm going to even zoom back out to show you the full geometry. Something I haven't showed yet. was that the geometry itself was only given in just the blades themselves were given. There was no geometry given for the hub or the shroud on either the rotor or the IGB. So there are tools in Pointwise to be able to create these kind of curves and work with this kind of missing geometry. This is kind of important for being able to deal with, you know, incomplete or dirty geometry. Let me go back to the rotor tip. And something I want to point out that's very specific to the fault-tolerant meshing idea, where you can mesh across faulty geometry, or maybe you just don't like the way that the geometry is laid out. You can see the blue lines here are the grid curves themselves. You can see how the blue lines don't necessarily follow the edges of the surfaces. You can see how I created these grid curves that kind of traverse the backside of the trailing edge. So essentially, the fault-tolerant meshing idea is saying you're not forced to put the curves on the edges of the surfaces. You can create curves that traverse surfaces, but are still constrained to the curvature of that surface. Another place I use this technique is at the leading edge of the tip. So let me move to that orientation. So you can see the seam and the geometry running down the leading edge is a little bit offset from the true leading edge of the blade. So I actually moved the connector slightly to the right, closer to the true leading edge, and I did this because it worked better for my topology and actually increased the quality of my mesh at the leading edge. And the last difficult feature of the tip gap area is the rounds. So I'm just going to turn the mesh back on, turn the geometry off temporarily. And we're going to look at the trailing edge region again. The orange meshes you see here are the boundaries of the block in the tip gap region, and you can see how I kind of have them bowed out to avoid the pinching of the edges of the round. If I ran these grid curves, straight up from the round all the way up to the shroud, due to the nature of the round, we'd have some pretty nasty pinching. And the way I did this was fairly straightforward Pointwise. This can be done with little effort using some of the curve modification tools. Again, I have a simplified example to demonstrate how this worked. So this is the cross-section of what I started with in the tip gap. So I need to, first of all, create the mesh itself. So the important thing to note is the mesh is really bad because of the pinching at the sides of the rounds. So the first thing I want to do is I want to stretch the curve on the shroud, and this is analogous. You can do the analogous step that I'm doing in 3D. But even after stretching essentially the shroud curve here, you can see there's still a fair amount of pinching in the corner. So what I'm going to do is I'm going to convert these straight curves into Bezier curves, and I'm going to move the control points to bow out the curves. I'll do it for the second one. And it's important to note when I do this is that because these are essentially internal grid surfaces, the precise location of where I move the control points is not that important. Really, I just want to move it such that I improve the quality of the mesh, so that it doesn't pinch so bad at the edges of the round. So again, let's just quickly check the quality of that mesh now. Let's look at it. The minimum included angle. Now we can see we have, a minimum included angle greater than 35 degrees. So I mean, if I would have showed it to before, it would have been, again, less than 1, which would have been bad. So I'm going to revert back to the 3D mesh to see how it turned out. So I'm going to look at the internals of the block in the tip gap region. So let's look at maximum clip angle. Let's turn off the color bar for now just to get it out of the way. You can see there's a similar effect that I achieved by bowing those curves out in the tip gap region. You can zoom in a little bit to that round. You can see how those, by bowing those curves out and also stretching the domain or the on the shroud itself helps significantly. And I just want to quickly comment about the tip gap mesh. The mesh I'm showing you here probably has enough points to capture the leakage loss, but there's probably not nearly enough to get vortical or cavitation losses. But the important thing to note here is it wouldn't be too hard to modify this mesh to get enough points in the tip gap to resolve these secondary losses. So if I just to briefly summarize what I just covered, your hands aren't tied by either dirty or missing geometry. Pointwise will always give you a way out. So we're finished with our high quality mesh, and now we want to get to the good stuff and run a calculation. So Pointwise can organize and save your grid in your solver's formats. So I'm going to show you how that's done. So the first thing you want to do is you want to pick your solver. You can see Pointwise supports a lot of different solvers. There's more than 30 different native formats. I'm going to choose OpenFoam, because that's the solver I use to do a calculation in. And I should make a quick note, you can also get your grid out in a few neutral formats, such as Plot3D or Nastran. And next, and probably the biggest time saver getting your grid set up for your solver is setting up the volume and boundary conditions. I'm going to show you how that's done. So we can see we have lists of these are groups of surface meshes, and then these are also physical types. And so if I just highlight, let's say, for example, the rotor inlet, I just pick that one, you can see it's highlighted 3 surface meshes that represent the rotor inlet. And now I can change the type, and these are physical types that are going to correspond to the CAA solver you picked. For OpenFoam, I just want to set it as a patch. Let's say, for example, that the rotor blade now, I want to change it. There's a wall type, etc. And just to show you how these physical types will change based on your solver, maybe I'll go and switch to a different CAE type. Let's go maybe to NASA Glenn's AdPack. Go back to the set boundary conditions. You can see how the groups have not changed. So if I look at the rotor, it still has the grouping is changed, but it's the physical types that have not changed, and that correspond to that solver itself. So let's just set it to inlet in the case of AdPack itself. So the last thing I want to mention about the CAA solvers is if your commercial solver is not in our supported list, or maybe your custom CFD solver uses its own format, you can create your own CAA export type and have it appear in Pointwise's CAE list. We've actually developed an API that lets users write their plugin so you can export your mesh to your custom CAE type. And documentation and software development kit are published on our website. And if you email me, I can point to the URL for that information. So I mentioned running a calculation using OpenFoam. Here's a snapshot of the solution, and what I'm highlighting here is the recirculating flow in the inside here at the root of the blade near the trailing edge, and I'm pointing this out because this was actually a notable flow feature identified in the experimental work. And I'd like to pass on a quick thanks to Eric Patterson and Brent Craven at Penn State University ARL for help with some of the OpenFoam turbomachinery tools. As I mentioned, the grids will be available for download tomorrow on our website in a couple of different formats. And just a couple quick statistics about the grids before I close. The IGV and rotor meshes each have about 800,000 hex cells, and I have the near wall spacing currently set to get a Y plus of about 30. That concludes my demonstration on some of the key techniques I used in Pointwise to create a multi-block structured mesh on the DARPA HIREP Pump. At this point, we're going to open up the virtual floor to you so you can ask questions about what you've seen here, or maybe you just have some other general questions about Pointwise. So Nick Wyman, our resident turbomachinery expert, will be fielding your questions. Thanks for your time and attention.
So if you have questions, there's two ways. You can still type questions into the question window there. If you want to ask a question using your microphone or telephone, use the hand-raising function, and I'll recognize you and unmute you, and you can ask whatever question you want. So I see one hand raised right now. Stefan, I think it's that cold, so I'm going to unmute you. Stefan, did you have a question?
I would say it was a very good presentation, and I have some problems with the commas, with the round commas, and I would say thanks for the help.
Oh, well, thank you. There was one other question that came up during the presentation, and that was, could you zoom in on the fillet block a little bit just to show what the grid looks like in there? So, Chris, do you think you could do that?
Yeah, absolutely. Just let me switch over to the mesh. So maybe I'll look at I'll show the rotor in this case. There we go. Move to a different location here. Maybe the other side. There we go. There's a better shot of it.
Okay, and we had a typed-in question. I sent that over to you, Nick, if you want to take a shot at answering the question about getting a lower Y plus value.
Okay, I'll answer that verbally, if you don't mind. The question is if we would desire to lower the Y plus value considerably, like an order of magnitude or more, would the dirty geometry issues cause problems in the mesh quality? The answer is potentially. In general, though, you're going to be okay because the meshing techniques that are used, for instance, the grid spacing techniques and the grid solver that Chris demonstrated, are all based on the discrete geometry, that is the grid, the resulting grid, rather than the underlying CAD. So typically the problem is that your gaps and overlaps can be on the order of your mesh spacing in the viscous direction. And the thing here is that you just need to be careful with the approximations that are done in the way that your mesh is draped over the imperfect CAD geometry. Essentially what our surface meshes do in that case is they locally are projected onto the CAD surface, and if you need to have a grid resolution on the order of those imperfections in the CAD model, you may need to take additional steps in the projection stage. There are some techniques that you can do. You can project onto the surface locally, or you can do a local approximation of those surfaces so that you're capturing the design intent without necessarily projecting onto the CAD that is so dirty. So there are a couple of different techniques, but those are the methods that we would use when we're dealing with dirty CAD, that is where the imperfections are on the order of the grid scale.
Okay, now we've got a question from Tim Beach. Go ahead, Tim. All right, I'm having a little trouble picking him up. Are you there, Tim? Okay, having some audio troubles there. I think I'm going to go ahead and mute you again. If you want to try typing in your question, you can. We've had a couple of other typed in questions that I'm going to let Nick handle. Do you want to answer the one about unstructured meshes, Nick?
Yes, there's a question that says, if your solver can handle an unstructured mesh, what would be the reasons for creating a structured block mesh? In general, a structured block mesh is going to be much more efficient, both computationally in terms of the number of cells and points required to get an equivalent answer to an unstructured mesh. But also, you tend to gain some accuracy simply due to the fact that when you lay out your topology, as Chris has done here, you create many grid lines and faces that are flow aligned, and those are going to minimize discretization errors for a given mesh size. So there are computational benefits to the structured mesh, but there is also an accuracy benefit. A third one that I would mention is that it is much easier to get a repeatable mesh character when you're looking at case studies for instance, for different changes in geometry. You want to compare results in a design study. You want to compare results on equivalent meshes so that you know that the changes in flow properties that you're seeing are not due to the changes in the mesh. This is a notoriously difficult thing to achieve with unstructured methods because an unstructured method builds itself up every time from the boundaries and is not quite as reproducible as a structured mesh. So that's another reason is when you're doing a design study and comparing results across different designs, a structured mesh is going to give you a better comparison. There's a second question came up about our topology in the rotor tip gap region. It says, I noticed that you have pole or singularity boundaries in the rotor tip. The question said near the fillet, but it's actually in the tip region. At the rotor fillet, at the hub, we do not have any pole or singular topology. However, in the tip gap region, there are poles or singularities running from the leading edge to the shroud and from the trailing edge to the shroud. And this was simply a simplification of topology in that case. Possibly you could use similar techniques to what Chris used to remove the poles at the fillet. You could use them to remove the poles at the leading and trailing edge in the tip region. However, in general, this is a technique that's been used in a lot of cases for tip gap regions to quickly and simply create a grid in this region. And it tends to not cause problems computationally because the area of the pole is 0, so you're not actually calculating any flow in that region.
Okay, I've got Tim's question now. He says he's curious about the leading edge and the tip clearance and wants to know what the grid looks like there. So, Chris, could you zoom in on the leading edge of the tip gap region?
Yep, sure. Just give me 1 second. Let me flip over. In the actual tip region, like closer to the leading edge.
Yeah, it says the tip leading edge. And,
okay. We just changed a different cut plane. So is that sufficient? Is there a different orientation they would like to look at?
Could you take a cut that's more horizontal, like that will show what the grid lines look like going into the poles? Yeah, like that. That should give some idea of what the topology is.
So essentially, they're in, the unstructured solver is going to see them as a wedge or like a prism. It's going to be like an extruded triangle.
All right, and we've got a question about the best way to import an AutoCAD geometry. Do you want to handle that one, Nick?
Yes. The question is what is the best way to import an AutoCAD geometry? I have tried an IGES import, and I lost part of the geometry. In general, we work with IGES every day at Pointwise, so we definitely have imported IGES from AutoCAD before. Pointwise's IGES import reader is fairly strong. However, there are a few limitations in the supported entity types from the IGES specification. Usually these are addressed by changing the options in the CAD system during IGES export. And in general, this would be a support issue that our support engineers could help work with you to get the best results with your combination of CAD system and Pointwise's IGES reader. So I would encourage you to take your individual question directly to our support engineer so that they could help you get the best conversion process.
Okay, we've got another question of someone wanting to see something else in the grid, and that is, can you demonstrate a more complicated elliptic smoothing for multiple domains? Perhaps go back to the 2D fillet example and allow all of the domain boundaries to float, and give an idea of what the grid would look like then.
Okay, I'll give it a shot. I haven't tried it, but let me go. Okay, so I'm back to my fillet topology example. I'll just kind of reset what's going on here. So this is kind of the unsmooth mesh, and so the question is, what would happen if I selected all the blocks and allowed them to float? Go to my edge attributes. I'm going to change it to floating. And again, the edges near the walls, I want to keep the spacing fixed, so I'm going to change the spacing to be my near wall spacing. So I just ran it like 10, so just to hop out, just see what it did. So you can see it now. In this case, it's allowing everything to float. So I'm not sure. I mean, this is probably up to the user to decide whether or not he likes this better or not. I mean, for such a simple one, maybe it seems to be clear to me at least that you would just want to keep the very perfectly orthogonal hub and blade block. But maybe in 3D, maybe this is a better approach. But there's no reason why you couldn't try it. And the analogous thing can be done in 3D, where I can let internal surface meshes float when you select multiple blocks to be smooth.
Okay, I see one last question about periodic boundaries. Do you want to handle that one, Nick?
Yes. The question is since the periodic boundaries of the rotor grid system are arbitrary, is there an automatic way to optimize the shape? The answer is yes. The floating techniques in the solver that Chris has demonstrated in the hub to shroud plane could also be done in the blade-to-blade plane. However, we typically, in our usage, don't do this simply because we find that you can sketch out a reasonable shape in a very quick time, and by keeping the topology relatively simply shaped, we find that it just makes it easier to go in and edit it and understand the grid topology when you want to change the grid dimension or something like that. But there's absolutely no reason you couldn't run the solver in a in the blade-to-blade plane and float the periodic edges to get a more organic shape there that would be maybe reduce some skewing. There are different techniques for doing so. You would possibly, you'd have to create a temporary copy of the blade-to-blade grid so that you would have its neighbor to base that smoothness off of for the shared boundary. And then the other thing I will mention is that Pointwise has a periodic linking feature. When you're creating periodic geometry such as the periodic planes, you can, for the case of one-to-one like Chris has done here, you can link those so that they remain a periodic transform both in shape and in grid dimension and distribution. So that's another time saving. So it's not necessary to create both copies of this grid. You can simply create one, and then the second is a periodic transform of the other.
All right, I don't see any more questions, and we're pretty close to the end of our allotted time today, so I think we'll wrap it up here. But again, thank you everyone for attending the webinar today. As Chris mentioned earlier, we're going to make the grid files and geometries and a recording of this video available on our website starting tomorrow, and that's just pointwise.com/webinar. If you have any questions, you can contact Chris by emailing sales@pointwise.com. And again, thank you for your time. Bye-bye.